1503. The Caribbean Sea. Christopher Columbus is on his fourth voyage. His fleet consists of 4 ships, and their objective is simple baseline survival. The fleet never makes it home. The structural failure was caused not by a tropical storm, a reef collision, or hostile artillery engagement, but by a passive acoustic signature, a soft, continuous grinding sound radiating through the hull planking below the waterline. It was invisible, constant, and internal. By the time the crew understood what was happening, the oak planks that held the ship together had been hollowed into a fragile shell, a honeycomb of tunnels carved by an animal smaller than a man's finger. The animal was called teredo navalis, the naval shipworm, and it didn't just sink Columbus's fleet, it sank empires. Now consider this. Your home sits on pressure-treated lumber soaked in synthetic preservatives. Your deck is sealed with petroleum-based coatings that peel within 5 years. Your foundation relies on Portland cement that cracks under freeze-thaw cycles and has to be patched, repatched, and eventually replaced. Every solution on the hardware store shelf was designed to be bought again. 600 years ago, Chinese shipwrights faced 2 enemies simultaneously: rot from below the waterline, fire from above it. And they found a long-lasting, highly effective answer to both using 3 ingredients they harvested off the beach. No mines, no smelters, no industrial supply chain. Minimal recurring costs beyond labour and locally gathered materials. By the end of this video, you will understand the exact chemistry of an ancient bioarmour called Chunam, a tung oil and seashell compound so structurally advanced that modern material scientists needed scanning electron microscopes to understand why it worked. It helped keep Admiral Zheng He's massive treasure ships afloat across 3 oceans, using materials that did not depend on mines, foundries, or European-style industrial dockyards. And the 1763 British Admiralty report, the one that documented the catastrophic failure of their own copper-sheathed fleet, proved that Western metallurgy had spent 200 years chasing a problem the Chinese had already solved. Stay with me. This is a story about engineering, not history. Teredo navalis is not a worm. That matters, because calling it a worm makes it sound manageable. Something you could poison, something you could scrape off, something that lives on the surface. It is a bivalve mollusk, a highly modified clam, and it does not live on the surface of wood. It lives inside it. The organism enters the hull in its larval stage, microscopic, free-swimming, invisible to the naked eye. Once it contacts submerged timber, it undergoes rapid metamorphosis. 2 small asymmetrical shells at its anterior end begin rasping against the grain of the wood. It drills inward. It never comes back out. As it tunnels deeper, its soft body grows behind it, sometimes several inches, sometimes over 3 feet long, lining the tunnel walls with a smooth calcium shell as it goes. The destruction is entirely from the inside out. A ship's captain standing on the dock could look at his hull and see solid oak, run his hand along the planking and feel nothing wrong. But 6 inches inside that wood, the structure had been replaced by a network of hollow tubes. The hull was not a hull anymore. It was a facade. The historical record on this animal is staggering. In 1503, it effectively crippled Columbus's fleet in the Caribbean, leaving his ships so worm-eaten that he and his crew were stranded in Jamaica and forced to abandon them. In the 1730s, a shipworm epidemic attacked the wooden piles holding the earthen dikes of the Netherlands together. The dikes began to fail. An entire nation faced catastrophic flooding, not from a storm, not from a war, but from a mollusk. The Dutch government commissioned emergency academic studies. Scholars scrambled to understand what they were dealing with. The organism had a tolerance for variable temperatures and salinities that made it nearly impossible to exclude from any harbour, any estuary, any coastal waterway in the world. For wooden navies, it was an existential threat, but here's what nobody talks about. The shipworm was only half the problem. The other half came from the sky. Ancient and medieval naval warfare ran on fire. Fire ships, small, fast, expendable vessels packed with burning pitch and combustibles, were standard tactical weapons. Incendiary arrows, Greek fire compounds, burning oil pots launched by catapult. A fleet that survived the biological rot of the ocean still had to survive the thermal assault of combat. And here was the engineering paradox that broke Western navies for centuries. The most common waterproofing material available to European shipwrights was boiling pine tar. It worked reasonably well against moisture. It was completely useless against fire. Pine tar is concentrated fuel. An incendiary strike on a tar-coated hull didn't just start a fire, it accelerated one. The ocean wanted to eat the ship from below. The enemy wanted to burn it from above. And the material protecting against one threat made the other threat catastrophically worse. That was the problem. Now watch how the British tried to solve it. By the mid-1700s, the British Royal Navy had concluded that the only viable defence against the shipworm was brute force. They would clad every warship below the waterline in solid copper. The logic was sound. Copper is a natural biocide. It poisons marine growth on contact, barnacles, seaweed, shipworms. It also maintains the ship's speed by preventing the biological drag that slows a fouled hull. And unlike pine tar, it doesn't melt in tropical heat. The industrial undertaking required to execute this solution was immense. Raw copper ore had to be mined, smelted, rolled into precise sheets, and transported to centralised naval dockyards. Only a wealthy global empire could sustain it, but the British had that empire, and they committed. In 1761, the Royal Navy fitted the 32-gun frigate HMS Alarm with 12-ounce copper plating, secured to the hull with iron nails. The ship was deployed to the West Indies, the most aggressive shipworm environment in the Atlantic. The experiment was considered a success. Then the Alarm came home. The 1763 Admiralty inspection found that the copper had worked exactly as intended against the teredo navalis. The biological threat was neutralized, but the structural integrity of the hull was failing at a rate that alarmed the inspectors. The copper sheets were detaching. The iron bolts and nails holding the ship's timbers together had, in the words of the official report, in many places wasted away into a kind of rusty paste. The British had stumbled into a new way to sink their own ships. They were only beginning to understand why. What they had stumbled into was galvanic corrosion, one of the earliest large-scale, clearly documented cases of bimetallic electrochemical failure in an engineered system. When two dissimilar metals make direct physical contact inside an electrolyte solution, and seawater is one of the most effective electrolytes on Earth, a battery forms. The less noble metal acts as the anode. It sacrifices itself. The more noble metal acts as the cathode. It is protected. Iron is less noble than copper. The iron bolts were dissolving to protect the copper sheets. And because the surface area of the copper was vastly larger than the surface area of the iron fasteners, the galvanic current was enormous. The bolts were gone in 2 years. The inspectors found one anomaly worth noting. A handful of iron nails were perfectly preserved, untouched. The inspectors traced the difference. Those specific nails had been accidentally wrapped in the brown paper used to ship the copper sheets from the foundry. The paper acted as a dielectric insulator. It broke the electrical circuit. The fasteners insulated by the shipping paper survived. Those in direct contact with the copper sheets degraded entirely. While the Royal Navy understood the basic mechanics of this insulation, attempting to scale it using tar-soaked paper failed over extended deployments, as continuous oceanic friction stripped the dielectric barrier away. The solution cost them decades and a national treasury. A fleet-wide refit in 1786 replaced every iron bolt with a copper-zinc alloy. Later, in the 19th century, they adopted Muntz metal, 60% copper, 40% zinc, to reduce cost. Each fix required the next fix. The bill never stopped growing. That is the pattern. Heavy industry creates a problem. Heavier industry is called in to solve it. The dependency deepens. The cost compounds. And the original problem, the biological threat in the water, was never actually solved. It was suppressed expensively, with materials that introduced new catastrophic failure modes. Now consider what the Chinese were doing while the British Admiralty was writing reports about dissolving bolts. The Chinese solution had 3 ingredients. The first was oil pressed from the nuts of the Tung tree, Alurites 4di, a fast-growing toxic plant native to southern China. The Tung tree was so central to the maritime economy of the region that during the Song dynasty, the major port city of Quanzhou was known as Zhutung City. The surrounding hills were planted with Tung forests specifically to supply the shipyards. The oil was not imported. It was not refined. It was pressed from local nuts and used raw. The second ingredient was slaked lime, calcium hydroxide, not quarried from distant mountains, not processed in industrial facilities. The shipwrights walked to the beach, harvested oyster shells, coral, and calcified marine debris, and burned them in coastal kilns. The ocean provided its own building material. The third ingredient was hemp or jute fibre, shredded, kneaded into the paste, providing tensile strength to the finished compound. Every ingredient came from within a half-day's walk of the shipyard. The supply chain had no weak links because it had no links at all. The compound they produced was called Chunam, and the reason it worked begins with a chemistry that most people have never heard of. Tung oil is classified as a drying oil. That term is misleading. It does not dry in the way water dries, by evaporation. When Tung oil is exposed to oxygen, it undergoes autoxidative polymerization. The high concentration of eleostearic acid in the oil, a polyunsaturated fatty acid with conjugated double bonds, allows the molecules to cross-link at a structural level. The liquid oil absorbs oxygen from the air and cures into a hard, flexible, completely waterproof polymeric matrix. But here is what separates it from every synthetic finish on the hardware store shelf. Modern polyurethane, modern varnish, modern epoxy, these materials cure on top of the wood. They form a plastic film over the surface. That film is rigid. Under UV exposure, under thermal cycling, under the mechanical stress of a flexing hull, it cracks. It peels. It fails at the interface between the coating and the wood. And once it fails, moisture gets underneath and the degradation accelerates. Tung oil has a low enough molecular weight that it penetrates deep into the porous cellular structure of the timber before the polymerization process completes. It does not coat the wood, it becomes the wood. The outer layer of the timber itself is transformed into a hydrophobic, structurally reinforced barrier. There is no interface to fail. There is no film to peel. But the oil alone was not the breakthrough. The breakthrough was what happened when it met the burned shells. When quicklime, the product of burning those harvested seashells, contacts moisture, it undergoes slaking, a violent exothermic reaction. Heat is released, the material expands. When the shipwrights kneaded raw Tung oil together with the lime and the hemp fibres, the calcium ions from the lime reacted with the fatty acids in the oil to form calcium carboxylates, a hybrid bond, part organic, part inorganic, that locked the two materials together at a molecular level. This was not a theory. In recent years, researchers have run thermogravimetric analysis on ancient Tung oil lime putties excavated from Chinese ship sites, including Ming period yards such as Baochuanchan in Nanjing, a shipyard associated with the construction of Zheng He's treasure fleet. Thermogravimetric analysis confirmed the enduring structural integrity of the calcium carboxylate-rich matrix. In one tested sample of centuries-old Chunam-type compound, the main structural degradation peak appears around 457 degrees Celsius, about 855 degrees Fahrenheit. For that material, the empirical mix optimized by historic shipwrights came out to roughly 1.4 parts slaked lime to 1 part raw Tung oil by mass. Not an accident, but the result of generations of refinement at that site. Here is the part worth sitting with. Modern scanning electron microscopy of that same centuries-old Chunam reveals a microstructure with extremely few large pores, a dense, tightly bonded matrix with very limited pathways for water ingress. Water penetration is drastically reduced and shipworm larvae find little exposed timber to colonize. The calcified, oil-hardened surface is simply too dense, too chemically foreign, and too mineral-rich for teredo navalis to attack easily, and yet the material is elastic. The interwoven jute fibers and the polymerized oil allow the hardened compound to flex dynamically with the hull as it pitches through ocean swells. Modern Portland cement, the material we use to build everything, would shatter under those same stresses. The ancient compound flexes. It gives, but it does not break. The waterproofing problem was solved. The biological threat was neutralized, but a ship that cannot burn is worth more than a ship that cannot rot. Chinese builders understood this, and they had already developed the thermal solution in a completely different context. In the densely built wooden cities of ancient China, fire was an existential threat. A single spark in a palace district could consume an entire city block before anyone could respond. To protect the load-bearing columns and beams of their most important structures, Chinese builders developed a surface treatment called Yima Wu Hui. The name translates roughly as 1 hemp, 5 ashes. The ingredients: raw hemp fibre, lime plaster, tung oil, and sometimes pig blood as an additional organic binder, applied in thick coats directly to structural timber. Transitioning this exact chemical configuration to maritime architecture yielded a highly resilient, protective coating. Modern material evaluations describe the cured Chunam and Yima Wu Hui matrices as behaving like passive, intumescent-style flame retardants, charring, foaming, and forming a protective mineral crust under extreme heat. That is a specific technical designation. An intumescent material does not simply resist fire. When exposed to extreme heat, it undergoes a controlled phase change. The surface chars. The mineral content transforms into a hardened, calcified crust. That crust acts as a thermal barrier, absorbing heat, blocking oxygen, and preventing the underlying material from reaching its ignition temperature. On a ship hull, the mechanics worked identically. A fire arrow strikes the Chunam-coated planking. The organic surface chars at the point of impact, but the calcium content of the compound, the burned seashell mineral locked into the polymer matrix, transforms the outer layer into ablative armour. The incendiary weapon is burning against a calcified shell. The heat is absorbed by the chemical phase change. The oxygen required for combustion cannot reach the timber beneath. The weapon burns itself out. The thermal degradation peak of the Chunam matrix, confirmed by laboratory testing, sits at 457 degrees Celsius, 855 degrees Fahrenheit. A pine tar-coated European hull would ignite well below that threshold. The Chunam hull would not. One compound, 2 threats, 1 solution. This is where modern engineers get it wrong when they look at ancient materials. They assume that a single material can only solve a single problem. The Chinese bioarmor solved biological ingestion, structural waterproofing, thermal shielding, and dynamic hull flexibility simultaneously, using ingredients that cost little and required no industrial infrastructure to produce. In the early 1970s, marine archaeologists excavating the mud of Quanzhou Bay in southern China uncovered a ship. It had been there since the late 13th century, around 1277 AD, preserved for roughly 700 years in the sediment. When they cleared the hull, they found something that changed the history of naval engineering. The ship was about 113 feet long. It had a V-shaped bottom, a heavy central keel, and 12 thick transverse wooden bulkheads, dividing the interior into 13 independent compartments. Every joint between those bulkheads, every seam, every interface between wood and wood, was packed with a dense filler. Analyses of similar sealing materials from Chinese ships show a lime and tung oil putty reinforced with plant fibres, a Chunam-type compound. The watertight bulkhead is one of the most important structural innovations in the history of naval architecture. A typical European ship of the same era had a largely open lower hold. One serious hull breach, one reef strike, one cannonball could flood the entire space. The ship sank. The crew died. The cargo was gone. The Quanzhou ship had 13 independent compartments. A breach flooded one. The other 12 held. The ship could limp to port on a fractured hull that would likely have sent a comparable European vessel to the bottom in minutes. Marco Polo wrote about Chinese ships with internal partitions during his travels in the late 13th century, likely referring to this same compartmentalized design. European navies would not widely adopt true watertight bulkheads for roughly another 5 centuries. Now scale that engineering to the early 1400s. Admiral Zheng He, 7 voyages, Southeast Asia, India, the Persian Gulf, the Swahili coast of East Africa, the largest wooden fleet ever assembled. The traditional historical records describe the largest treasure ships, the Bao Chuan, at around 417 feet long, with 9 masts. Modern engineering analyses, working from the constraints of wooden hull physics and surviving evidence, tend to place more conservative estimates in the 200 to 250 foot range. Even at those lower figures, they dwarf anything sailing in European waters for another 4 centuries. A wooden vessel of that length faces a structural problem that has no modern equivalent. The hull must flex. Ocean swells apply enormous bending forces across the length of the ship. A rigid hull snaps. The Chunam putty, elastic, dense, permanently bonded to the timber, allowed those massive hulls to flex dynamically without losing structural integrity or watertight sealing. The 1.4 to 1 lime to oil ratio found at the Baochuanchang shipyard in Nanjing, the yard that built these ships, was not a general purpose formula. It was an engineered specification for vessels operating at the absolute limit of wooden hull construction. And then there was the supply chain. That is not a small thing. A British warship that lost its copper sheathing in the Indian Ocean faced a journey of thousands of miles back to an industrial dockyard. Months of transit, months of repair. The ship was vulnerable the entire time. The cost was enormous. The dependency was total. A Chinese junk with hull damage beached on any tropical island. The crew walked the shoreline, collected seashells, built a fire, burned the shells to quicklime, mixed the lime with the tung oil and hemp they carried in the hold, and packed the breech. The salt air and tropical sunlight polymerized the patch within hours. The ship was back in the water. That is a global supply chain that fits inside a sailor's pack. The ocean that threatened the hull also provided the material to repair it. The same coastline that harboured the shipworm also harboured the oyster shells that turned the shipworm from an existential threat into a manageable problem. In 1424, the Yongle Emperor died. The political factions that had opposed Zheng He's voyages moved quickly. Funding for the great expeditions was reduced, key shipyards were scaled back or closed over time, and many naval records and plans were allowed to decay or were deliberately discarded. The hygiene policies, sea bans restricting private maritime trade, were reinstated and in later reigns expanded. Long-range oceanic ventures were curtailed. The greatest naval technology on Earth was sidelined not because it failed, but because the institutions running it collapsed inward. The cutting edge is pointing backward. The chemistry of Chunam did not disappear. It was set aside, and the difference between those two things matters enormously to anyone paying attention to what is happening to modern supply chains, modern material costs, and modern institutional reliability. Pure tung oil is still available, not the blended hardware store version. Those products mix raw tung oil with synthetic varnishes, polyurethanes, and metallic drying agents to accelerate curing time. The result is a plastic film that peels. The pure version, the one the Ming Dynasty shipwrights used, relies entirely on natural autoxydative polymerization. It contains no volatile organic compounds. It does not off-gas. It penetrates rather than coats, and it is still being used by restoration carpenters, timber frame builders, and craftsmen who have rediscovered what the Song Dynasty already knew. The lime oil putty formulation is directly applicable to modern off-grid construction. Waterproofing wooden water cisterns. Sealing foundation timbers against ground moisture. Creating fire retardant coatings for structural beams in wooden buildings. The calcium carboxylate chemistry that held Zheng He's fleet together across 3 oceans will hold a homestead together across a Montana winter. The recovery is just beginning. Small craftsmen are bringing the technique back. Material scientists are publishing papers on centuries-old putty and finding that it outperforms modern synthetic equivalents in flexibility, longevity, and biological resistance. The institutions that replace this knowledge with expensive industrial dependencies are not going to tell you that. But the chemistry does not lie. The Chinese did not beat the shipworm and the fire with heavier industry. They beat them with a deeper understanding of what nature had already provided. A polymerizing nut oil, a mineral pulled from the sea, a plant fibre that grew in the field next door. 3 ingredients, 1 compound, 2 threats eliminated. The British spent decades and a national treasury chasing the same protection with copper, iron and steam, and triggered a cascading electrochemical failure that nearly dissolved their fleet from the inside out. The Chinese had the answer figured out with materials a sailor could carry in his pockets. The point is not that the old way was simpler. The point is that the old way was complete. Most of what this channel covers works exactly like that, not forgotten because it failed, but set aside because something heavier and more profitable came along. If recovering that kind of knowledge matters to you, subscribing is the simplest way to make sure the next story finds you.